lesson 10. And we're going to talk all about solely today ionic compounds. Okay, ionic compound structures, what they look like, etc., etc. All right. So I'll let you guys copy here, and then I think you guys have the first part there, I think. I'll let you guys copy that, and then we'll take a quick little. So, ionic bond, of course, is a very strong chemical bond. Results from the mutual attraction between cations, positive ions, and anions, which are negative ions, of course. When in their solid form, the ions join together in what's called a crystal lattice structure. The crystal lattice is common for all ionic compounds. So when I talk about sodium fluoride and sodium chloride and potassium sulfide and calcium phosphide and whatever else, magnesium nitride, they all look like this, okay? They are all alternating three-dimensional arrangement between cations and anions. What does that look like exactly? Well, it looks kind of like this stuff here, all right? So alternating, all plus-minus attractions, okay? Some of the things that you're going to talk about later on here, I'm just going to jump to it right now here. So remember, all positives, what makes them so strong is a network of this positive-negative ions. So all positives are attracted to all negatives around it, including this one down here, okay? Every negative is attracted to any positive that's around it, okay? So for example, like that there, all right? And as you can imagine, there's going to be a few, and when I say a few, I mean a few cajillion attractions here. There's going to be lots, yes? And that's why ionic compounds are found in solid form, right? Because all these attractions make it a very strong, hold it together very well, and therefore, as a result, are usually found in solid form. So look, attraction, attraction, right? There, there, and there, etc., etc. Okay? And there's tons and tons of attractions here. All those positives are attracted to all the negative. Every ionic compound looks like that. Ionic crystal lattice. Okay? Crystal lattice structure. Alternating three-dimensional array there. Here's a few more examples here. Okay? What you have to keep in mind is it doesn't matter really about the formula. So if it's calcium 2 plus and F minus, it doesn't matter if it's CF2. It still opposites attract. Okay? That's all it is. So like I said, they all look pretty much the same. Okay? I'm going to stop you here for a second. Okay. So this strong network of ions influences many of the properties of ionic compounds. Right? They're very strong. So that is a part of these positive-negative attractions. Ionic compounds have very high melting and boiling points, and we're going to revisit this later. This is important. Significant temperatures are required to provide the energy needed to break apart the crystal lattice. You need lots of energy to break apart that opposites attract, plus, minus, alternating three-dimensional. Okay? So, very high melting and boiling points. Lots of attractions, stick together very well. Takes a lot of heat to melt an ionic compound. Takes a lot of heat to boil ionic compounds in some cases. Many ionic compounds are easily dissolved in water due to the polar, there's that word, polar nature of water. What does polar mean? What does it imply? Polar, what does that mean from yesterday? Anyone? Polar. Yep. Yeah. The partial positive and partial negative, yes? Water is a polar molecule. It has a negative end to it and a positive end to it. And we're getting there eventually. That's going to be our next lesson starting, well, not tomorrow, but the day after probably. All right? So water is a polar molecule. Many ionic compounds can dissolve easily in that water because it's polar. Well, I'll show you that later, actually. And finally, the last one here. Ionic compounds can act as electrolytes when dissolved in water or when melted. At this point, the ions are free to move around, allowing for the conduction of electricity. Electrolytes means conductivity. Okay, conduction of electricity. One of these two things are very important, by the way. Ionic compounds can act as electrolytes when dissolved in water or when melted. So when you change it from solid form to liquid form, they're very good conductors of electricity. Or if you put them into water, they can act as electrolytes. They don't have to. Well, they all will to certain degrees. We'll talk about that a little later here. Okay? Ionic compounds, this is important as well, do not conduct electricity when in solid crystal form. So when they're in a solid form, they do not conduct electricity. Okay? Think about, you have to have a freedom of motion. We have to have some positives and negatives that are free to move. When are they going to do that? In water, to different degrees, in water, and in when you melt them, they're going to have some freedom of motion. In solid form, they're all connected together. There is no motion. There is no freedom of motion. So therefore, they do not conduct electricity in solid form. Only in liquid form. Okay? Actually, they're pretty good. They're very good in liquid form. In water, it varies. We'll talk about that in a few minutes here. Ionic compounds are brittle. If you bend them or chisel them, they will break. Okay? So, even though ionic compounds are incredibly strong, they're at the same time very brittle if you hammer or stress them. Okay? And I'm going to show you why in a second here. So, ionic compounds are made up this alternating three-dimensional positive, negative, yes? I can't draw three-dimensional. I can barely draw two-dimensional, as you'll soon see. However, very generally speaking, that would be an ionic compound of some sort. Opposites attracting to each other, etc., etc. Here's the thing, though. That's incredibly strong. That holds together very well. It holds together so well that all ionic compounds are in solid form. You can go in the back of the chemistry lab and see. They're all in solid form. They hold together very well. Opposites attract, solid form. However, they're also very brittle. If you take a hammer, don't laugh. What? It's a hammer. I don't think I have to explain that. I just said that. Okay. You know what? There's some racing stripes. Okay? That's the handle part. And don't try and show me up with your hammer on the test or anything like that. Okay? Hint, hint. Because that's, you know, that just doesn't make me feel good at all. So, I got one drawing one time. It was so awesome. Like, the hammer was like an actual hammer. Like, I could have cut it out. It was awesome. Anyway, and then they was like, check out this hammer. And then I was like, 0. When you hammer or stress, I'm going to use a hammer for example, what happens? Well, you get this kind of thing here. Oops. And if you guys have ever played with magnets, and you should have at some point in time in your life, if you haven't, go buy some. They're fun. All right? They attract each other. When it's like this, you know, they attract very well, right? What happens when you turn the magnet and you try to push it together? What actually happens? They repel, right? They push away from each other because like charges have come together now and they repel each other. Try it if you don't believe me. If you've never played with a magnet, my goodness, go get one. They're awesome. You can just simply do this all day and then turn them around and try and push them together and they just don't go together. It's just like like that. It's funny. Like, it's seriously, that's what I did last night for 2 hours because I have no friends. But when you hammer them, here's what happens. You actually shift, okay, those positive and negative ions. You shift them in a way, and guess what? Like charges become aligned. And when like charges become aligned, they tend to break in a smooth line, okay? We say they cleave in smooth planes because technically this is not a line. This is a three-dimensional object, yes? So when we talk about planes, we're not talking about airplanes. We're talking about board kind of thing. That's a plane. they tend to break in smooth planes. Okay, so cleave or break in smooth planes or lines. Planes is a three-dimensional line, of course. Okay, so they break like that. They cleave or break in smooth planes. All right. So as strong as they are, as soon as we start to stress them or hammer on them or whatever the case might be, okay, bend them, if like charges become aligned, they're going to break. Okay, especially when enough of those, like if two become aligned, is it going to break? Probably not, because 2 out of kajillion is not really that much. But if you get a million or a billion out of kajillion, kajillion's a made-up number, then probably, yeah, there's a chance that they could break or cleave in a smooth line. Okay, so that's why they're incredibly strong, however, at the same time, very brittle. All right. So that's this right here. All right. Moving on here. Ion attractions are non-directional. In other words, all positive ions attract all negative ions. I think we already know that, but just going back to here for a sec, right? Every positive is attracted to every negative around it, and every negative is attracted to every positive around it. And guess what? You get a network, right? So you get, well, not there, I guess, but you get this network, right? So think about in this cube here, how many attractions would you have? Lots, yes? So that's what gives it that property, of course. Very good at attracting each other, et cetera, et cetera. There are no distinct neutral molecules in a compound, in ionic compound. So when I talk about sodium chloride, somebody would say, well, yeah, let's go back to my drawing here because it's so awesome, especially the hammer. When you talk about sodium chloride, there's no distinct sodium chloride. So you might say, well, there's sodium chloride there. And then I'd say, nuh-uh, it's right here. And then, well, Stephanie, of course, would say this one, because why wouldn't she, right? We all know, right? So everyone would come up with a different sodium chloride. There's no one molecule, okay? They're just a bunch of positives and negative ions attracting each other. And like I said, there's tons of them, right? So et cetera, et cetera. Let's see, what else do we got here? Yeah, and then the formula is just the formula. It's the simplest ratio, okay? But all of them eventually turn out to be this crystal lattice structure. Opposites attract. All right? I think that's it, eh? We're good? Okay. One more thing, though, we need to talk about here. Yeah. We talked about, and I'll probably refer to this again. So I kind of thought, well, should I do it now or not? But you know what? I think I will. Give you an introduction to it kind of thing, a review kind of thing, and then I think later on we'll probably end up doing this again, and that's fine. But when we talk about these ionic compounds, you need to get your periodic tables out. When we talk about the solubility, for example, of ionic compounds, you can just write this on the last you can write this on the last sheet of your notes there. This is not going to take a lot of room here. When you talk about the solubility of ionic compounds, we have a chart for that. It's on the back of the periodic table. And there was one thing that we did talk about here, and that's why I thought maybe we should talk about this right now. We should maybe understand how this solubility chart works. Most of you guys used this last year, yes, solubility chart. So you're probably okay, but just a quick refresher. Basically how it works is we have kind of 3 rows here, okay? This is your very soluble row, and this is your slightly soluble row. And then up here, of course, we have a list of ions here across the top, right? And if you look at those ions across the top, most of them are negative, yes? Okay. Now I'm going to tell you, you know, for example, I'm going to give you one here. We're going to do sodium chloride. Sodium chloride is an ionic compound, so it technically is a solid, right? We're talking about salt here, yes? If we take sodium chloride and we dump it into water, okay? That's water, by the way. If you don't believe me, I'll do it in blue, okay? Water's blue. Actually, it's clear. But anyway, water, okay, what does water look like? Well, going back to some of the notes here, the reason I'm going to do this here is because water kind of looks like this here. And of course, you're going to have lots of waters in here, yes? Right? If you look at any water bottle there, right? How many waters are there in there? Probably lots, yes? So there's lots of water in there. If you dump sodium chloride into there, well, before we get to that part here, let's look up sodium chloride as whether it's very soluble or slightly soluble on your ionic chart there. What do? Well, sodium chloride is made up of sodium ions and chloride ions. And if you don't know how this chart works, please, please, please make sure you do after this. All right? If you have to, separate them into ions. Usually, you look for the negative ion first across the top. So, you got your little chart here, okay, like this. Look for chloride across the top here, right? Chloride is also with bromide and iodide, by the way. So, you look for that one across the top. You find it. Good. Okay, here's my chloride. So, where is this now is the next question. And when you look at chloride, it says most here, and then it's got a list of some ions down here. So what you need to do is find out where that sodium ion is, the Na+. Is it listed down here in this row here? Do you see it there? So therefore, by default, okay, if it's not listed here, it's got to be in the most category, okay, because it's not here, so it's got to be in the other part. So sodium is actually up here, which means sodium chloride is very soluble, right? This is the very soluble row, right? Straight across. Sodium and chloride is very soluble. Yes? True? Okay. When you put salt into water at home, yes, what happens? It dissolves, right? It disappears. Why does it disappear? Well, you're taking a solid, right, and you're putting it into water. What's actually happening? What's actually happening, and there's a name for this, but I'm not going to get into that right now. That's going to be Unit 3. What actually happens is when you put sodium chloride into water, turns out water is polar. Do you remember that? That's from the notes today. And we'd have some partial negatives and partial positives on that molecule. And you don't have to understand how that molecule is polar. We're getting there. You're going to do that eventually. Water's polar. So the negative end of water, that partial negative end of water, is attracted to the sodium ion. So there's an attraction here between this end of water and the sodium ion. And it basically pulls sodium chloride apart from each other. Okay? The chloride end is perhaps attracted to another, doesn't have to be the same water molecule, it could be a different one, but it's attracted to the positive end of that water molecule. And water breaks that ionic compound apart. All right? Basically, breaks it apart. That process is something called dissociation. Breaks into ions again. So even though ionic compounds are very strong, at the same time, you put them into water, water is able to pull them apart because of the polar nature of water. Okay? So it pulls that apart. That's why it becomes very soluble. Right? Very soluble because soluble implies that it's broken up, okay, into sodium ions and chloride ions. Can you see sodium ions? Can you see sodium ions? Can you see chloride ions? No, right? Can you see sodium chloride together as a solid? Yes, that's what you start with. You put it into water, water breaks it up into sodium ions and chloride ions. That's what happens when you put salt into water. That's the process. That's why it disappears, okay? Because you can't see the individual ions of sodium and you can no longer see the individual chloride ions. They're not combined together anymore. They're broken up, okay? Now, if you look at a different example here, so that's very soluble. Calcium sulfate, for example, is also obviously a solid. Let me get my water out here. Okay. when you look up calcium sulfate, you know, say the two words, calcium sulfate. You're looking up calcium 2 plus and sulfate 2 minus. Find SO4 2 minus across the top. Okay? There is only, it's all by itself there across the top. Always look for the negative ion first, across the top. Up here, it says most, I think. And then there's a list of some ions down there. Where's calcium 2 plus in that top part or bottom part there, Stephen? Bottom. In fact, it's right here, yes? Calcium 2 plus, right there. So that tells you that it's slightly soluble. Slightly soluble. And we're going to talk about the definition of very soluble and slightly soluble. But what that generally means is that, yes, in fact, some of the calcium sulfate will break up, but not very much at all. Okay? When you put calcium sulfate in the water, what generally happens, okay, is it actually goes right to the bottom and it stays stuck together as a solid. And we call that a precipitate. Right? It does not break up into ions. You will actually see the calcium, it's a white substance. You'll actually see it just go straight to the bottom. It'll go, you pour it in the top and it goes right to the bottom and sits there. Okay? Have some broken up in there. Is there some calcium ions and some sulfate ions? And the answer is yes, there is. How many? Not many. Okay? But that's why we call it slightly soluble, because only a few break up, not all of them. Okay? Or most of them, for that matter. So only some break up. Water, turns out, is still in here, of course. It's still obviously polar. Water, in this case, not strong enough to break up that calcium to sulfate ionic bond. Okay? So in this case here, water's not strong enough to do that. That's why it stays together, and that's why it floats to the bottom or sinks to the bottom, and that's why you'll see calcium sulfate at the top in a bottle, and you'll see calcium sulfate at the bottom of this water stuck together still. Okay? Water's not strong enough to break that apart. And that's what that chart basically means. Now, one more thing. If we go back to the notes here, it says, where is it here? Okay. Ionic compounds can act as electrolytes when dissolved in water. Okay? What that means is they will act as electrolytes in water, but to different degrees, right? When you think about electrolytes, you know, what conducts electricity very well? What conducts electricity very well? Positives and negatives, yeah. And the freedom of motion. Do you think, okay, that sodium chloride, is there going to be a lot of plus minuses in sodium chloride? Lots of ions. Yeah? So is it going to be a good conductor of electricity? Absolutely. So, not only is it very soluble, but that row also implies it's a very good conductor. Or you could say electrolyte for that matter. Okay? Those are very good conductors. That top row is the ones that are going to conduct electricity very well. If you look at this one, very good conductor or electrolyte, if you look at this one, how many free ions are you actually going to get from calcium sulfate? Probably not that many, yes? Most of it's going to stay together, like calcium sulfate. It's going to sink to the bottom. Do you have free ions in this case? No, obviously not. Do you have many? Is there some? There is a few. Okay, there always is. How many? Not many at all. So we would say that this is actually a poor conductor or a poor electrolyte. Now, there's always exceptions to every rule, but if you assume that we're taking the same amount and all that other stuff, okay, generally speaking, the bottom row is not as good of a conductor. It will still conduct electricity. Maybe in some cases barely, but it will. Okay, they're good. They're always conductors, but there is a variance, right? Very good, lots of separation, lots of positive negatives. Poor, okay, not many. Most of it stays together, okay? And that's all I have to tell you about that. So those are ionic compounds. Make sure you look over those notes again, and make sure you understand what ionic compounds are and some of the properties of them, because it's very important for later on here, all right?